All right, welcome to this explainer. Today, we're diving into a total game changer from Skip Uni's Lecture-34. We're looking at how arrays are passed in C++. You know, if you've been scratching your head over how to properly pass array by reference in C++, well, you're in the right spot. We're going to break down exactly what happens with arrays passed to functions, how an array as function argument really works behind the scenes, and the super tight connection between arrays and pointers in C++.
But first, let me ask you a quick question. Are you accidentally cloning your data? Seriously, when you pass an array into a function, do you know what actually happens to your computer's memory? A lot of folks, especially when they're starting out, kind of just assume the system photocopies everything they send. But think about it. If that were true, large programs would literally crash from memory overload in seconds. So let's figure out what's really happening under the hood.
So here's our game plan for this explainer. First, passing arrays to functions. 2, call by reference explained. 3, the base memory address. 4, array pointer arithmetic. 5, why array size matters. And finally, number 6, getting ready for advanced algorithms.
All right, let's kick things off with part 1, passing arrays to functions.
So if you want to do anything useful with an array in a separate function, like, sorting it, searching through it, or modifying it, you can't just toss the data at the compiler and hope for the best. Here is rule number 1, and it is absolutely crucial. Arrays are always passed by reference. Yep, when you're dealing with arrays in C++, no duplicate copies are ever made. It's kind of the most important concept we're talking about today. Think about it. If you pass a massive array with, say, 10,000 elements into a function, the compiler doesn't waste time making 10,000 brand new copies. It does something way smarter, and honestly, way more efficient.
Which brings us to section 2, call by reference explained. To really wrap our heads around this smart transfer, we've got to separate passing by value from passing by reference. Think of call by value like making a physical photocopy of a document to hand to someone else. If they spill coffee on their copy, your original's totally fine, right? But call by reference, that's sharing the exact original memory address. Because the function gets a direct line to the original memory location, any tweaks you make to the array inside that function will instantly and directly alter the original array back in your main program. There is no photocopy safety net here, guys. You are editing the live document.
Moving right along to section 3, the base memory address.
The real trick here is understanding how C++ actually looks at the name of an array when it sets up this call by reference. The base address is just the exact memory location of the array's very first element, what we developers call the 0th index. By default, when you pass an array by just typing its name, you're literally just passing a pointer to this 0th index. So let's say your computer stores the start of your array at memory address 1000. When you pass the array's name into your function, you are handing the function the number 1000. That's it. That is the whole secret to how arrays move around your program.
And because of this, we've got a little syntax secret. Typing int array square brackets is exactly the same as typing int.starArray with a pointer asterisk. Since the array is passed and treated entirely as a pointer by the system anyway, both of these syntaxes mean the exact same thing to the compiler when it catches that function argument. You can write it either way. Under the hood, the compiler is just looking at that base memory address.
Okay, section 4, array pointer arithmetic. Let's make this super concrete. Picture an array named number that holds the elements 10, 20, 30, 40, and 50. How do we actually step through all those elements if the function only got the starting address? Well, let's walk through the pointer math line by line. If we just use the name number, we get the address of the first element, let's call it 1000. Now, by slopping on an asterisk, the dereference operator, making it star number, we fetch the actual value sitting at that address, which is 10. So how do we move forward? Easy. Number plus 1 shifts the memory address forward to the second element's location. And finally, star number plus 1. You put the asterisk outside the parentheses, and boom, it grabs the value of the second element, which is 20. Add a plus 2, you get the third element, and so on. You know, we are literally doing math with memory here, which is pretty awesome.
Now for section 5, why array size matters.
This brings us to a huge, critical, missing piece of the puzzle. If we're doing pointer arithmetic and we only have the starting address, how does the function know when to stop? The source lecture uses this fantastic analogy for this. Think of your memory as a long street of houses. Passing the array name only gives the function the address of the very first house. But if the street has 10 houses on it, giving someone just the first house's address doesn't tell them where the street ends. If they just keep adding +1 to their address, they'll just keep walking down the street forever, eventually reading random data that doesn't even belong to your array.
So the big takeaway here is that without passing the size, your traversal loop is gonna fail. The function only knows that starting address. It has absolutely zero idea how many elements it's supposed to visit. If you want to use a standard loop to navigate, like a classic for int I equals 0, I less than size I++, it needs a hard limit. Passing a size variable, like the number 5, is strictly necessary alongside the array name. That way, the function's traversal loop knows exactly how many elements to print or modify safely without going out of bounds.
Let's see how this plays into dynamic size calculation. Because hey, you don't always have to hard code that size variable manually. In your main program, you can actually figure this out with a little simple math. Step 1, grab the total memory your array takes up using size of number. Step 2, get the memory that just a single element takes up using size of int. Step 3, just divide the total by the single element, size of number divided by size of int. This instantly calculates the total number of elements in your array. It gives you the perfect size variable to pass into your function dynamically. Pretty slick, right? And finally, Section 6, ready for advanced algorithms.
Let's zoom out for a second and look at why mastering all this low-level memory management is so vital to your coding journey. Everything we just covered today, it is the absolute foundation for the next steps in data structures. Safe array traversal, linear search, binary search. Literally none of these advanced algorithms work unless you perfectly understand call by reference, base addresses, and why you absolutely have to pass the array size. You've got to know how to cleanly and safely navigate the memory before you can build complex algorithms to search it.
Which leads us to our final thought. Now that you hold the exact map to your memory, what algorithm are you going to build first? Realizing that you aren't just moving abstract data around, but actually pointing directly to the physical fabric of your computer's memory, man, it unlocks a whole new level of programming power. Take these concepts, go practice your pointer arithmetic, and I guarantee your C++ functions will never be the same. Thanks so much for joining me for this explainer, and happy coding.